is if I told you that the derivative of some function was that our derivative is secant squared of 5x, then you need to be able to quickly recognize that, hey, secant squared, that's the derivative of tangent. So that must kind of be the base function that we're working with. But that 5x inside, we're also going to have to take care of. So when we're taking the derivative of something, we know that we have to use chain rule. And when we're taking the antiderivative, we sort of have to undo that chain rule. So to find my function here, I'd be thinking, okay, well, I know that tangent has a derivative of secant squared. So let's assume that it's tangent. But I know that my trig, the taking derivatives can never change the argument of my trig function. It can't change what's inside, which means that that had to be a tangent of 5x. So if this is my guess, then the way that I would check my guess is by taking the derivative of it. Well, if I take the derivative of tangent of x, I'd end up with, not tangent of x again, if I take the derivative of tangent of x, I'd end up with secant squared of 5x, and then times, because of chain rule, I'm going to have to multiply that by 5. This 5 isn't there in our original derivative that we started with, which means that we're actually going to have to correct for it in our guess for the antiderivative. And the way we're going to correct for it is by dividing by 5. So it turns out that the correct antiderivative for secant squared of 5x is tangent of 5x divided by 5. And then we're going to remember to add the plus c for a constant. Similarly, if I had that dy dx was equal to, let's say, cosine of 3x, then when I take the antiderivative, I'm thinking about who's the function whose derivative is cosine. And the function whose derivative is the function whose derivative is cosine is sine. I know that I can never change the argument for a trig function, and I also have to correct for the chain rule, which means this is going to look like sine of 3x divided by 3 plus a constant. Now, this idea of sort of dividing out the chain rule piece, it only works if your chain rule was going to lead to multiplying by a constant. We'll have more complicated ways of dealing with it down the road if what's inside of your argument is more complicated. But this dividing by a constant thing, it works for trig functions, and it also works for exponentials. There seems to be less glare on this half of the board, so I'm going to try to use this half of the board a little bit more. So thinking back to 17a, if I had a function like e to the 5x, then when I take that derivative, I'm going to end up with e to the 5x times 5. Which means that if we flip this around and we're thinking about antiderivatives, if I started out with something where dy dx was e to the 8x, and I'm trying to find the antiderivative of that, then my antiderivative is going to look like e to the 8x divided by 8. So that I'm undoing that chain rule piece, plus a constant. Should I keep going with more antiderivatives? We can do some messier algebra ones. So again, you can either raise your hand or give me a yes on your screen, that check mark. Okay, let's do a couple more. Let's do some messier algebra kind of antiderivative problems. And I will say that we're going to spend probably at least 3 weeks working with antiderivatives. So we don't have to be an expert on them right now. We're going to develop more techniques for finding those antiderivatives. And at any time, if you want to hit that raise hand button, let me know. I'll try to kind of keep an eye on the screen so you can interrupt me. So let's talk about so let's say that I told you that, and I'll actually write an instruction. So we're going to find the antiderivative. So if y prime is equal to, I'm going to scoot that down just a little bit. So if y prime is equal to 3x squared plus 7 square root of x all over x to the third. And what I've been asked to do is to find the antiderivative. If I were doing this, and for those of you that know me from 17A, let's pretend that I was looking at this problem and I was asked to take the derivative. For those of you that know me from 17A, I would not do a quotient rule on this problem. I would look at this problem and say, is there some way that we can simplify the algebra first to make the whole thing look like a number times x raised to a power? The same thing is going to be true if I'm finding antiderivatives. My first step is going to be to say, can I make this look like a number times x raised to a power? So here, I'm going to take that and write it as 2 separate fractions. So that first fraction, I've got 3x squared over x cubed, and then plus 7, and I'm going to go ahead and take that square root of x and rewrite that to say x to the 1/2 power. So I've got 7x to the 1/2 divided by x cubed. I haven't done any calculus yet. All I'm doing is rewriting the algebra of the problem. I'm going to do one more step to rewrite this to simplify those exponents. So 3x squared over x cubed. 2 of those x's are going to cancel out, and I'm going to end up with 3 over x. Now on this part over here, I'm going to have to subtract those exponents, and I'm subtracting fractions. So if I come off to the side here, I'm going to have 1/2 minus 3, but in order to subtract that 3, I need a common denominator. So that 3 I'm going to multiply by 2 over 2. And I'm going to end up with, it looks like -5 halves. So when I simplify this, that's going to look like 7x to the -5 halves. I could have left that as an x to the 5 halves in the denominator, but that wouldn't really help me to find the antiderivative. Now this one I left in a particular form because I'm hoping that we look at that and recognize, oh, we know whose derivative that is. So the function whose derivative could be something over x, and in particular, if I rewrote this to say 3 times 1 over x, then the function we're looking at, whose derivative is 1 over x, is natural log. So finding that antiderivative, this is going to look like 3 natural log of x plus, now this one is already in our form where we have a number times x raised to a power. So finding the antiderivative means I'm adding 1 to the exponent and dividing by the new exponent. So I've got x. If I add 1 to the exponent, I'll be at -3/2. Then I'm going to divide by the new exponent. And finally, add in a plus c. Because regardless of what that constant is, when I take the derivative of it, it was going to go to 0. So no matter what that constant is, it would still match the original derivative. And there's one other subtle thing that we're not really going to connect back together until 5.3. But in section 4.6, where there's the list of antiderivative rules, we want to be careful when we're finding the antiderivative of 1 over x. And what we want to make sure that we're able to preserve is the domain. So if I think about 1 over x, the only value that we're not allowed to plug in to this is 0. We can plug in both positive and negative values. So in order to preserve that domain when we're finding the antiderivative, we say that the antiderivative of 1 over x is natural log of absolute value of x. And we'll talk more about that a little bit later after we've discussed the fundamental theorem of calculus. But for now, just know that the antiderivative for 1 over x is natural log absolute value of x. The next problem I want to do is we call an initial value problem, or finding the particular solution for one of these antiderivatives. I'm about to erase this, so if anybody has questions, now's the time to hit that raise hand button or type anything in the group chat before I erase it. Okay, I'm not seeing anything, so I'm getting rid of it. So I'm going to switch the instructions now to say, find the particular solution. And I am going to give us a problem that looks like dn dt is equal to n times 1 minus n over k. And I'm going to say that n of 0 is 10 and that k is a positive constant. And I wrote or equal to, I didn't really mean to. We're going to say that k is a positive constant. So solving this differential equation, and by the way, what makes it a differential equation? There's a derivative and an equal sign. So solving this equation is the same thing as asking us to find the antiderivative. So I lied. I messed up the notation over here. I actually meant for this to be a function of n. So I'm going to rewrite this and make this dr dn. Sorry about that. So this is the same thing as asking us to find the antiderivative. When we're taking derivatives, we have a product rule. Here, we don't have a product rule for antiderivatives. So instead, we have to think first, this is only algebra, which means can I multiply this out, and in this case, make it look like n's raised to powers. So if I distribute that n out, so I've got dr dn is equal to n minus 1 over k n squared. Now I've got the whole thing looking like number times n raised to a power. We can go ahead and find the antiderivative and say that r is equal to, Well, so if I'm integrating n, and that's my variable that's acting like x right now, currently the exponent is an invisible 1. So if I add 1 to the exponent, I'll end up with n squared, and then we'll divide by 2. Here, I've got to keep that k around, so I'm going to leave that in there as 1 over k, add 1 to the exponent, divide by the new exponent, plus a constant. Now, I just made this problem up and I realized that I probably want to fix this. So I want this to say that our initial condition, which is generally what's going to let us solve for C. So I want our initial condition to be that R is equal to 10 when N is equal to 0. So I'm going to take that initial condition and plug it in anywhere that those letters show up in our general solution. So if I replace R with 10 and I replace N with 0, or should we make it more interesting? Let's make it more interesting. Let's replace N with 1. So our initial condition in this case is that R is 10 when N is 1. So now if I plug in 1, I'd have 1 squared over 2 minus 1 over k times 1 cubed over 3 plus that constant. Now I intentionally made this algebraically a little bit messy, but we're going to survive. So 1 squared is 1, so that's just a half. So I've got 10 is equal to 1/2 minus 1 cubed again is 1, so that'll be 1 over 3k plus that constant. And the idea here when we're finding a particular solution is that we're trying to come up with a value of the constant to plug back in to our general solution. So this one right here would be our general solution. So we can decide how much we want to do in terms of the algebra, but we can just rearrange this to make it say C equals by subtracting the 1/2 over and then adding the 1/3, the 1 over 3k rather. So I would get C is equal to 10 minus 1/2 plus 1 over 3k.